your kind introduction. You kind of anticipated some of the smorgasbord of the things I will talk about today. Thank you very much. So what you see here in the title is actually the same title I gave my Nobel lecture, because it's my personal voyage in part through these things. What you see here actually is a telescope on the Canary Island of Tenerife, and you see a green laser light going over there. We used this to test quantum communication with the island of La Palma, 144 kilometers, and on the other end of that laser beam is the Jacobus Kapteyn telescope. So I had a connection with Kapteyn over indirect connection over quite some time. I have to learn how to operate this. So here's an overview to put things into perspective. As you all know, quantum physics began in 1900. Actually 1899, but that's an interesting historical remark, not known by many physicists. Already in 1899, Max Planck had his quantum of action. It's quite interesting, and the reason why is also interesting. But anyway, with Max Planck and with Albert Einstein in 1905, these were two cornerstones of introducing the idea of the quantum. It took then 25 years until the theory was developed by Heisenberg and Schrödinger. And in 1930, around 1930, plus minus, a debate started. This is all a very nice theory. It describes nature very well. But what does it mean? What is it all about? And this is partly the story of my personal career, to investigate and experiment what happens. In the old ideas, people had Gedanken experiments. They said, okay, suppose I have an individual particle, what would happen? It was not possible to do these experiments in the old days. This changed in the 1970s with the development of the laser and with high flux reactors for neutron beams. These were fundamental experiments. We were lucky to be among the people who started this. And the groups at that time were very small. It was 1,000 people all over the world. And we were all considered to be a little strange, to be interested on these just philosophical questions which one shouldn't worry about. To the big surprise of all of us, in the 1990s, new ideas were born. The concept of quantum information was created. I will say a little bit about that. And suddenly, the stuff which we worked on in the 1970s seemed to become useful in a new technology. And this happens in science quite a number of times. And I want to point here already now that we have an unfortunate development in science worldwide, which is justifying research by possible applications. And this is short-sighted. That way, if we miss the fundamental work, we might miss out on some interesting further developments. Now, there were ideas like quantum computer, quantum communication, etc., etc. And since about 2020, and I wrote this slide, I wrote around 2010. So it was clear that in 2020 you will have some technology emerging, and there are companies now developing all kinds of things. So I would like to go on now. This is kind of the basic Gedanken experiment. That's a picture drawn by Niels Bohr. There was a big debate beginning, as I mentioned, in 1927 between Albert Einstein and Niels Bohr. The position of the two is, in short, very easy to explain. Einstein claimed all his life that physics and all science, by the way, has to be about what is real, has to describe reality. And Niels Bohr said, no, science can only be about what can be said about reality. And this is not an empty empty question, and I will come in the end on some modern meaning about that. In this experiment, it's the famous two-slit experiment. You have light incident from the left, so this first slit, then it can pass through the other two slits, and because light is a wave, you get these darkened bright stripes because the wave extinguishes or enforces itself from the two slits. And the question raised actually by Einstein already in 1909 is what happens if I if I make the intensity so low that only individual particles go through at a time. Would the stripes emerge if I collect many on a photographic plate or not? And Einstein said, no, it should not emerge because a particle has to go through one of the two slits. And how should it know whether the other one is open or not? And at that point, Einstein was wrong. The experiment was later on done with various kinds of radiation. What one talks about now is that we have a superposition of both possibilities. It would be wrong to say that the particle goes through two slits, but we have a superposition of both possibilities, and we only get these interference stripes if there's no information anywhere in the universe, be it on the particle or be it somewhere else, which would allow you to tell you where it went through. So this is actually a case where ignorance becomes power. Ignorance, objective ignorance, nobody knows, not even God knows, leads to something new. Now, here is an experiment we did in '88 with neutrons, rather heavy particles. Your body is made up. The largest number of particles in your body are actually, protons and neutrons. They actually have a very common particle. And we sent these particles individually through double slits, and we get these stripes here, one particle at a time. A collaborator here was Cliff Schall. You mentioned him. My then supervisor and then colleague at MIT, who got the Nobel Prize in '94. There's actually a tradition because when Schall was young, he worked with Arthur H. Compton, famous American physicist, for the photon scattering at electrons. So here's an experiment. You might now ask, how big can objects be where you can do this two-slit experiment? Is there a limit? And my assumption is there is no limit. It's only a question of ingenuity and money, how big you can be. So we did an experiment that's already quite a while ago with fullerenes. You see an artist's rendering of these molecules to the right. He was a former student of mine, Julian Foss-André. So these big molecules in a two-slit assembly, and there has been further development. Objects become larger and larger, and this is a field of very active research. How large can we put the limit? And I keep claiming that it should be possible to do it also with living systems, like with nanobacteria and so on. You just have to be clever enough how to do it. So in principle, there is no limit. And I'm saying this because it is wrong to say that the realm of quantum physics is limited to the small. Usually people say micro is quantum, macro is classical. This is not the same. This is not right. Quantum is a new way to talk about the world with new kinds of phenomena. Here's the famous Schrödinger's cat. I show it because you all have heard about it. And there is a famous statement by Feynman, one of the most popular physicists from America, who once said, "Never underestimate the pleasure of an audience hearing something they already know." So I tell you here about the Schrödinger's cat. It's a famous story. The poor cat is in a chamber with some poison in this green stuff, and there is an atom, a radioactive atom, which might decay or not. And when it decays, it releases a hammer, and the poison is set free with like cyanic acid or something, and the poor cat dies. And if not, after some time, the atom is in a superposition of decayed and not decayed. Just like the two slits, the superposition of this and that. So this is for sure, this is quantum mechanics, no question. And Schrödinger says if quantum physics is universally valid, then it should also apply to the cat. And the poor cat should be in a superposition of both possibilities, which means not that the cat is alive and dead, but it's only the superposition. Nobody knows in the universe whether it's alive or dead. Don't ask me about the poor cat, if the cat should know it. Schrödinger said this is a bizarre consequence, but he does not say that this is impossible. He is very often wrongly represented. So I was saying that this, to shift the limit up and up is an active research area right now worldwide. Just to say a little bit more about randomness. Zufall is also in Netherlands, you say toeval, right? Or something like that. T-O-E-F-A-L or something like that, Zufall, right? Randomness. Here's an example of randomness which can easily be understood. Suppose I have some light coming from the source here, and it hits what is called a half-silvered mirror, which is a mirror which reflects half of the light and half of it can go through. Just imagine you standing in front of a shop, the window of the shop. Sometimes you can see inside and you see yourself. So this is a half-silvered mirror. So if the light comes, half of it is reflected, half of it goes through. Then what happens if you just look at one single particle of light, one single photon? What does it do? It cannot be divided in two because quantum physics is against it. And there have been experiments that this is not happening. Now, is it reflected or is it going through? The answer is that it is in a superposition of both possibilities until you measure it. In a moment when you measure it, say it's reflected, then the whole state, so to speak, collapses. The other detector immediately knows, no matter how far it is away, that it should not detect the particle. So this is already some kind of non-locality, and as far as we know now, to me this is one of the deepest findings of science in the 20th century. This is randomness without any hidden explanation. It's not that we don't know why it happens. We know that there is no deeper explanation. And this is related to Bell's theorem and this kind of thing that we can argue this. So randomness is not just ignorance. Nature is random, and actually to a more significant degree than people would like to realize. But that's a different story. Einstein didn't like that. He said God does not play dice with the universe. He believed in that. To which Niels Bohr answered, stop telling the Lord how to run the universe. That's a very good answer. I mean, if there was ever a scientist who had the right to tell the Lord how to run the universe, then it was Einstein. Right? But anyway, I would give a lot to hear Einstein's opinion today about this situation. That would be quite big, because it's Einstein wanted science to describe what's going on. He wanted science to describe whether the particle is reflected or not. And we say, no, this is not possible, the information doesn't even exist. So that relates, the superposition relates directly to the notion of quantum information. In classical information, represented by this switch here, as an example, the switch is either on or off, 0 or 1. And we call this 1 bit. You know, we all use the word bit all the time. We buy computers because they handle more kilobits than before, but nobody knows what that really means, but it doesn't matter. But we buy, if the number is higher, we buy a new computer. That's a different story. So a bit is 0 or 1. The interesting point is now, in a quantum bit, you can have the two in a superposition. It can be superposition of 0 and 1. So in a sense, I put it under quotation mark, it is 0 and 1. And in a deeper sense, one calls this a qubit, a quantum bit. This superposition actually is much more complex than a classical bit. And that means that you can do things with it which you cannot do with the classical bit. The idea came from, the name comes from Ben Schumacher, a colleague at a small college in the US. So far we talked about two concepts which I want you to remember, and you should not fall asleep tonight because you worry about superposition and you worry about randomness. The third concept is entanglement. Already mentioned shortly in the introduction. It goes back to this famous paper by Einstein, Podolsky, and Rosen in 1935. And the idea is that they consider two particles which came from a common source or have interacted. And according to quantum mechanics, there can be situations such that none of the two particles after the interaction share a well-defined state. It's like if you consider billiard, for example. There's one ball is going this way, and the other one is going this way. In quantum billiard, both balls would be in a superposition of all possibilities, but they would be perfectly correlated. If you measure one, it is you localize it, it's here, and the other one is localized opposite, but it's wrong to think that they had this property before. Einstein realized that there was this perfect correlation without any connection between the two, and he called this spooky action at a distance, and he had very deep, very good reasons not to believe in it. The question is still open. I will say something about it. Schrödinger introduced the names Verschränkung and entanglement to that. I found out that in Dutch it's called verstrengeling, quantum verstrengeling, or something like that. And this is it is like if you had two dice. You have two dice, like you throw them, and one shows a 6 and the other one shows a 6, because they are perfectly correlated. Then you throw them again, and then you see this gets a 3, but the other one also gets a 3. And then you throw again, 2, whatever. The individual result being random, but the two perfectly correlated. And Schrödinger said, and what could be the explanations? The explanations could either be that there's some hidden mechanism which we don't know in the two, which gives the same result. And the second one is that there's some information transfer. And the story of this last Nobel Prize is that there has been a series of experiments which excluded these explanations. Schrödinger already realized, he said that I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. The two possibilities which we have, but I said it already now, is either we have to give up that the systems have their own reality, or we have to give up the two locations in space in this sense are separated. And the language physicists use, they say that the quantum states of the particle is actually not defined in real space, but in something much more complicated called configuration space. But this is just for the physicists among you to tell you that I know what's going on here, actually. So how to do an experiment? The classic experiment now to do these days, and these are experiments you can do in a student lab. We have this actually in a student lab where people can play with that. So that is standard now. You have a source which emits two photons, which are entangled in polarization, say. By the way, any property can be entangled now. Not only polarization, but whatever you call it. Energy, frequency, momentum, you name it, it can be entangled. But the most easy way to do it is to have entangled polarization. Polarization is the way how the electric field oscillates. And you can have a situation where you measure the polarization with modern polarizers. Polarizers you know from sunglasses, but you also know it from photographers know it, the polarizing filters. You can have polarizers where the two polarizations are separated. The one which goes up is horizontally, the one which goes down is vertically. And you can have situations where you have perfect correlations, which means that either both are horizontally polarized or both are vertically polarized. Now, one might think that this happens because they have been born that way. Yeah, but the polarizers, you could orient differently, both of them. And you will still, at 45 degrees, and you would still have perfect correlations. So how would the source know which kind of polarization it emits? That's an interesting question, right? And here comes Bell's inequality. Again, the same kind of arrangement, and John Bell, Irish physicist, 1964, realized actually that, in principle, the photons could have been born with all these properties, but he realized that if you measure one, vertically and the other one at a slight angle, you don't get perfect correlations anymore. But in quantum physics, the two results are more strongly related than in any classical model. And that's the story of the experiments to confirm this that this happens indeed in nature. In our case, the source is what's called parametric down conversion. I show you this picture because it's just beautiful, number one. And number two, what you have is you have called a nonlinear optical crystal. It's a special medium where whenever light comes into a medium, it excites the electrons there. And in a nonlinear medium, the response of the electrons is not directly proportional to the intensity which comes in. And then you can have a situation that an incoming photon, UV pump here, creates two photons. And the two photons can come out in these rings depending on their color, and they are correlated with each other. And there can be situations where the two photons, all the two photons know that their polarization has to be different, but they don't know which one they have until you do the experiment. Okay, this was actually a part of our developments in '95. When we embarked on these experiments in the 1990s, we didn't have any idea how to do it. But then, over the time, we developed our methods. So here's again the idea of John Bell. You have a source, and you can measure polarization along A or B, and you get the result, red or green, on either sides. And the first experiment was done by Friedman and Clauser. Clauser was a co-Nobel Prize winner recently in the early 1970s. And Clauser only could do the experiments in a little laboratory in the basement in University of California in Berkeley, because he had a generous professor who said, you do something else, but you can also have this little laboratory for that stuff, And John Clauser he was really kind of considered a crackpot. Never got a regular position at the university. So he later on lived independent from other sources until this day. Aspe, when he did these experiments about roughly 10 years later, Aspe told John Bell that he wants to do more precise experiments about this. And the answer of John Bell was immediately, do you have a permanent position? No, otherwise you might run into problems. So he did his experiments. So the experiments over the time realized these correlations, and they Widerlegung, they showed that local realism is not possible. The idea that reality is local means not independent one side from the other, no instantaneous communication. Here is how simple an experiment looks like. That is actually the experiment we showed at Documenta. You have the blue pump. In this thing where the red beams emerge, the red beams are then the two entangled photons, and then you can couple them into glass fibers and look at the correlations. Now, to say again what is going on, one assumption is Einstein locality. Namely, I showed this intentionally in German because I understand that Dutch is very similar to German. The measurement results are independent of what happens at the same time, at the distance. That's the point. At the same time, at the very same time at the distance. Okay? Specifically, what you get here is independent of what measurement somebody over there decides to do. Okay? Which is a reasonable assumption. This comes from Einstein. And the second idea about realism is that the results of your experiments correspond to properties which the system you observe carries or carried before and independent of observation. You reveal some property. These are the two assumptions, So it's the idea of a world out there and the passive observer. You just look out there and you realize the properties. The two assumptions together don't work, and my more romantic position is that both of them are wrong. Both of them are wrong. Now, how does a modern experiment look like? Like we did, this is already 98, but this is still the standard. We create a pair of photons, send one with a glass fiber over to Alice, the other one over to Bob, and then you see here electro-optic modulator. Then we decide at the last moment which polarization to measure, because we want to exclude the possibility that one side tells the other one what is being measured. You know, there could be some hidden secret communication. And any communication has to be, we'll know that from relativity theory, is limited by the speed of light. So what we do is in the very last moment, we change the polarizer. So if there was a communication to the other side, it would have been wrong. Right? And the way, how do you switch? You cannot change it. You know, when you in Innsbruck we did this experiment over 300 meters, which means that we talk about microseconds of communication time. So you have to change the polarizer in microseconds, but that cannot be done. You cannot rotate something in microseconds. But the way you do it is that you have a special crystal called electro-optic modulator, and when you apply some voltage, the rotation axis is changed. So we apply some voltage in the very last moment, and that is decided by what is called a random number generator. So in that experiment, we have a random number generator which actually uses remember the half-silvered mirror before, uses this kind of half-silvered mirror. But this is all very nice, but there are still limits in that kind of experiment. I will tell you about that right away. By the way, one can apply this to, for example, cryptography. Oops. No problem. I'm not too old to okay, anyway. Enthusiasm, yeah, it's enthusiasm. I'm still enthusiastic about this stuff. Yeah, when you create many pairs, I told you, and you measure the same property on both sides, you get a random number. On one side 0 or 1, on the other side 0 or 1. And if you measure many, then you get here a random sequence of zeros and ones, and you get here a random sequence of zeros and ones. But the two random sequences are entangled. They are identical because of entanglement. So what you then can do is you mix the information you want to send from A to B with your random sequence. And then the spy has no idea, no possibility to find out what was sent. But the receiver, Bob, can easily decode it. And that was our demonstrations then of quantum cryptography with entangled photons. up there you see the two keys, Bob's key and Alice's key, the random number sequences. And what is sent was this picture of Venus of Willendorf. It's a famous picture found near Vienna, about this big. And you know why we use this picture? Because my students came to me and said, okay, we have to use some picture to really demonstrate convincingly what's going on. And they came to me with a picture of a bomber or a tank and so on. And I told them we have to find something which is number one, Austrian, and number two, with no doubt, not a symbol of war or something like that, peaceful symbol. So we chose this Venus of Willendorf. And that was actually published in Physical Review Letters, which is the American journal, where that's still the best physics journal in the world. And I was actually expecting that the Puritan Americans say, no, you cannot do that. But they didn't say anything. They accepted it, you know. So, okay, that's the way it is. Now, so far we talked about two-particle entanglements, and this subtle question about Bell's inequality, which that you have when you have the correlations, two polarizers not oriented the same way, but at slight angle to each other, that the measurement results are stronger related to each other than in classical physics. Now this is a subtle point, but in 1988, Greenberger, Horn, and myself discovered that the situation is even more striking if you have three or more particles. You can have the situations that, you know, you have three particles and you measure their polarizations, horizontal and vertical, just as before. You can have a situation, for example, that when you observe one of them to be vertically polarized, say number one, number two, also vertically polarized, that quantum mechanics definitely says the third one is also vertically polarized, and the local realist, to a rather simple argument, would definitely say, no, it's horizontally polarized. So it's a contradiction on the individual particle level, which is actually in itself interesting, and these states have now, as was mentioned in the introduction, have now become a cornerstone in quantum computation, etc., etc. Here are my two friends, Mike Horn and Danny Greenberg, a little later at some conference some fundamental conference. Now, I want to say one thing. In 1988, from 1988, when we found this, it was my goal to realize that experiment. Okay? And it took us 10 years. And when we started that experiment, we had no idea how to do it. Absolutely no idea. How to make a source of three particles, how to measure this, and all this. And it took 10 years. And I say this because today, very often, when you apply for money, you have to tell the goal, and you also have to say how you want to achieve the goal. And that would have been absolutely impossible for us. And I emphasize, and I tell it to politicians, I tell it to everyone. If you want to have something really interesting, don't ask how somebody can do it. Okay, so that's the GHZ story. Okay, wait a minute, I hit the wrong button here. I'm sorry. I come now to teleportation, which is a rather popular topic, as I know, in this kind of things. Teleportation comes from these movies. They're very famous. They are in Star Trek, you know. And by the way, you know why teleportation was invented in these movies? Does anybody know? It's to save money, to make the film cheaper. You know, because otherwise, you know, when the starship arrives at the distant planet, you have to film how it lands, you have to simulate all that. It's very expensive. But if you just beam somebody up and down, it's cheap. You know, you save production costs, you know. And yeah, beam me up, Scotty, this kind of thing, right? And just to be now serious again, what is the concept behind it? The concept is that you have an original object, that you somehow read out the information, the complete information which characterizes the object. Then you transfer the information, and then you reconstitute the object with that information. And the point now is that according to Heisenberg's uncertainty principle, you cannot determine, it's impossible to determine the state of an individual system without errors. And actually without significant errors. So the people who did this film, they were told that it doesn't work. So I don't know who remembers that from these films. They invented the Heisenberg compensator. It's a good idea, right? And Gene Roddenberry, who was the mastermind behind this film, was once asked in a press conference, how does the Heisenberg compensator work? And his answer was a classic, which I think every politician or everybody can be proud. He said, very well, thank you. Now, like often in medicine, the cure comes actually basically from the same method, from the same kind of idea where the problem comes from. So the cure comes from quantum physics. You can't teleport the quantum state of a system. The quantum state of a system is the information which the system carries. You can teleport the quantum state of a system directly using entanglement from A to B, because in that case you do not determine the information. You just transfer it. Heisenberg says you cannot determine the information, you cannot know it. But if you don't have to know it, if you just send it from A to B without anybody knowing, then there's no problem. The way how this works is, this was invented by these 6 people here, shown on the picture, together with Schrödinger's cat, who seems to be, no, actually not alive. But you never know. The idea is that you have an auxiliary pair of photons, here called the entangled pair. And then you have the initial state, which comes from the left. And then the trick is that you entangle. There's a lot of entanglement going on now. You entangle the original one with one from the pair. Which means that the information about the original is actually lost. They don't, the individual photons don't carry any information anymore. But it is transferred over to the other one of the entangled pair, without ever being determined. Okay? That is the basic idea. When this came out in 1993, our reaction was, this is a typical, I apologize, a typical theorist's idea. It cannot be done. That is absolutely impossible. Not realizing that, I told you, from 1988 on, it was my goal to do the 3-particle entanglement. Not realizing, by working towards 3-particle entanglement, we were actually developing the concepts for teleportation. Okay? So this is another interesting. So then we did teleportation, which was just an off-spin of the whole thing. That's how it looks like on the experimental table. I don't want to go into details here, but it's not very many optical elements there. So that's the beautiful thing about the experiments which we do, that they can be done in very small groups and with in principle relatively little effort. So I want to come. I don't know how much time I have now. Oh yeah. So okay, I will come. Yeah. I come to one point which is interesting, conceptually very interesting. So far we have entanglement because the 2 particles came from the same source. Okay? And then at some point, we asked ourselves, but does this always have to be the case? Do they have to come from the same source? And the idea of what's called entanglement swapping says, no, this is not necessary. You can have 2 sources where each one creates an entangled pair, 1, 2, 3, 4. and then you subject 2 and 3 to a measurement which tells you that 2 particles were here, but it doesn't tell you which was which. They lose their identity in that measurement. It's quite a tricky concept. But by losing the identity there, then the 2 and 3 are measured such one measures the 2 photons, but such that one doesn't know and nobody knows from which source it came from. And in that very moment, 1 and 4 also become entangled, even as they had no source and nothing. So this tells us that entanglement is a general concept, and that's actually, to me, that is one of the most interesting concepts. So I want to come to some broader applications. Here is one experiment on the Canary Islands. I showed you the picture before between La Palma and Tenerife over a distance of 144 kilometers, all kinds of things, teleportation, etc., etc. And all this works nicely, and I want to come now to one interesting question. And that is, when you look back at this experiment, we had a random number generator which decides on this side randomly what should be measured and on the other side randomly what should be measured. Now, but wait a minute, in principle, there could be a common influence which influences the 2 random number generators. How can you exclude that? Well, you can exclude that by taking sources of randomness which are as independent as you can. And this calls for cosmic sources. So in this kind of experiment, also on the Canary Islands, where we actually used the William Herschel telescope, it belongs to the family where the Kapteyn telescope also stands. On the other hand, the Telescopio Nazionale Galileo, TNG, Italian telescope. Both are 4-meter telescopes, so rather big. And the 2 telescopes looked at different quasars. Quasars are supposed to be precursors of galaxies and so on. Very far out. One of them was 12 billion light years out. 1 quasar over there, 1 quasar over there. And we looked at fluctuations of the light coming from the quasars and took that as sources of randomness. And that decided in the last instance how to measure what kind of entanglement is measured. Now, this puts any possible, so any possible common inference would have been much earlier than these quasars. That puts things very, very far back, but not quite to the Big Bang. So you still can be working on it. So we are working on this and trying to use a cosmic background, etc., etc. Here, that's the last experiment I show. It is fun, but I should come to an end slowly. Right. That is the experiment which we called the Big Bell test, challenging local realism with human choices. So randomness so far was always something physical. The random number generator, or the light from stars, or the light from quasars, or whatever. Well, John Bell already said, wouldn't it be interesting to have the choice of humans, of people, to decide what measurement to do? Because he argues quite correctly that the assumption that human decisions, the free will, that we have a free will where we can decide independently, is actually central to do any science. Because suppose your decision which experiment to do would be predetermined, what's the point of doing the experiment? That could be completely misguided. It would end the whole fun. So what happened in that experiment was the following, that we took human choices to decide what to measure. Human choices in the following way, that there were 100,000 people could download some software on their mobile phone, and they could type in random numbers in the sequence, 0, 1, 1, 0, whatever they want. So that, okay, 100,000 participants, which created about 100 million random numbers. And the random numbers were uploaded into a cloud and were then distributed to 13 experiments worldwide. Yeah? All this happened happening within 1 day. And here it is, 100,000 human participants, 100 million binary choices, 12 laboratories, different kinds of things, and so on. And lo and behold, we get a violation of Bell's inequality. The next step now, but you know, there could have been something fishy going on, because this was not really over large distance. So the next choice, which is actually pursued by the Chinese, is to do the experiment with humans on the moon. And then even go further. If they ever go to, I keep saying for many years, if people ever go to Mars, then you know it takes about a year to go to Mars. They are utterly bored, so they might as well do a Bell experiment on the way to Mars. You know, that's one of the possibilities. So this is the big Bell test, just showing it the different blue colors. The different laboratories which participated all over the world, etc., etc. Here's just a picture to tell you how far we are going to the space. There was a satellite launched by the Chinese. It's called the Mizhou satellite, and that established, for example, collaboration between Austria and China over entanglement over 7,600 kilometers. I come to the end of my talk. The big question, which drives me and drove me, is the question: why the quantum? Why do we have quantum physics? The theory is absolutely fantastically confirmed by experiment, and it's of immense mathematical beauty. It's unfortunate that to see this beauty one has to learn some mathematics, but it's incredible how beautiful it is. Okay? But the question is, what is the deep reason? What is the deep reason why we have quantum physics? And there a guide point is Niels Bohr, who said, I mentioned in the beginning the debate between Einstein and Bohr. There is no quantum world. There is only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics is what can be, concerns what we can say about the world. And I turned, together with my colleague Czeslaw Bruckner, we turned the thing around. Maybe this is much deeper. Maybe what can be said about the world determines what can be real. Okay? So in that case, information would not be a secondary concept. And that was actually written down in an edition of the New Scientist quite a few years ago. They had the headline, "The idea from which all reality flows," is the idea that information is the irreducible kernel from which everything flows. And the kind of catchword is to say, in the beginning was the bit, you know. There is one of the Gospels, it says, in the beginning was the Word. But this is just, okay, this is an interesting parallel. So the idea is, what is the relation of reality and of information? Supposedly, at one point, Albert Einstein asked Niels Bohr, "Do you really believe that the moon is not there when nobody looks?" And Bohr said, "Can you prove the contrary?" Okay. This is just a joke, but there's something very deep in it. Yeah. I claim that the reality without the possibility of information about it makes no sense. And I suggest that we are now talking, and this is an emerging field where more and more people work on, is that we have to unify the concept of reality information. You know, very often in physics we had unifications. Like Newton unified the laws of physics on the Earth and in the cosmos. Maxwell unified electricity and magnetism and so on. Einstein unified space and time. And I claim that you have to unify reality and information. I want to conclude. Einstein said towards the end of his life, he make this very nice statement: I want to know how God created this world. I'm not interested in this or that phenomenon. I want to know the thoughts, the rest are details. And I thank you for your attention.
Thank you very much for a very inspiring lecture, right?
Thank you.
Very inspiring. And now we have time for questions. So, who would, ask the first question to Professor Zeilinger about his talk?
Thank you. Thank you very much for your talk, Professor. Sir, is it better there? Yeah. It was very interesting, and I think you have a very good way of explaining extremely complicated topics in quite simple manners for what they can be said. My question to you is that at the beginning of your talk, you mentioned about going from quantum, was sort of the quantum world into the macroscopic, and that we shouldn't so much think of these two things as separate. But that gets a little bit confusing for me when I think about, for example, the concept of quantum tunneling. Like, would you then assume that a tennis ball could bounce through a wall if we hit it enough times? Or what is it specifically that you mean with this sort of increase between the microscopic and macroscopic connection? Thank you.
Yeah, this is a very good question. What really, to what extent can quantum phenomena happen? The tennis ball going through the wall is most certainly a very unlikely phenomenon, right? Likewise, the interference of people going through two slits is a very unlikely phenomenon for various reasons. The point is that to observe quantum phenomena, you have to isolate the object from the environment. So you have to isolate the object from the environment such that this is called decoherence, that by interaction with the environment, it loses its perfect quantum state. This is one thing. And the second point is that in order to have a quantum state of a complicated object, like a human or like a cat, this means an immense amount of information. So what we do, classical physics, is actually not knowing more about the system, but knowing much less than what is possible. And that is a development going on now. About the tunneling, yes, this is extremely unlikely. But who knows? And not about the tennis ball, but maybe we will see things. People have now realized quantum superpositions of objects which consist already of 10 to the 20 atoms. So these are starting to begin objects which you can see in the microscope, and that is actually quite interesting. And you could see, my proposal is one could even see systems of living systems like nanobacteria if you isolate them sufficiently from the environment. And that could be done, I think, in the 100 years or whatever with nanotechnology. So my suggestion is one should try to find out. Even for the fullerene experiment, when we published that, there were papers by people saying that it will not be possible to observe this because it's so big and because of that and that. And when I read such papers, they are always correct. But you have to think about the assumptions. Maybe the assumptions which the people argue can be circumvented, and that is actually a research program.
Next question.
Hello, thank you so much for your talk. I wanted to ask, because you said something about the fact that it's very easy, or it's relatively easy, to use polarization as the property that you're measuring for the entangled systems.
Can you hold your microphone a little closer?
Okay, can you hear me now?
Yes, better.
Yeah. So I was asking, why is polarization necessarily a relatively easy property to measure when it comes to entangled systems? Because that's a statement that you made at the beginning of the talk. Why aren't you measuring something else?
Well, we actually, polarization is very easy to produce for practical reasons and to measure it. Actually, one of my things together with Horn was in 85 or whatever. We proposed an experiment where you can have entanglement of momentum, of particles, and that was actually realized later on. It's a little bit more challenging than the polarization. You can actually observe, and this is standard, entanglement of frequency of photons, entanglement of color. So you have two photons, where one can be blue and the other one is for example, red. And you can have the two photons such that none of the two photons know whether it's blue or red, but they know that they have to be different, for example. And there are also experiments about spin of electrons. There are experiments where people entangled something like 1,000 atoms with each other and so on. Also, all this goes on and is an active research program.
Can I ask a question?
Sure.
You talked a bit about a qubit at a certain point, right? Now, the lifetime of a qubit, right, is really restricted by decoherence. So my question is, is there any effect of decoherence on entanglement?
That depends on the system you use. The advantage of photons is that they do not interact with the environment. So there is no, otherwise you wouldn't see the stars and so on, that is quite clear. Yes, if you have systems which interact with the environment, like atoms, for example, then it's much more challenging. Then the atoms can emit radiation, for example, or they can absorb radiation, or they can be scattered. Light can be scattered from the atoms, and that rapidly destroys the entanglement. So this is really a challenge. It's also a challenge in quantum computation when you have many atoms, or you have many superconducting qubits or whatever. They can interact with the environment and lose their entanglement. This is one of the big challenges.
Okay, I think it's time for about the last question.
I have a brief, sorry for my voice, is a continuum or a continuous situation automatically a situation of entanglement?
I didn't understand.
Can you repeat the question a bit louder?
Hold your microphone, make it closer.
Is a continuum or a continuous situation, is that automatically a situation of entanglement? So I mean a continuum, like
a continuum of
a
what?
human body, for example, as an entity, or a part of the universe which is consistent, more or less.
I don't understand.
It's a difficult question.
Sorry.
I think the question is not very clear. So maybe, let's say we go in a minute, we go downstairs, right, for a drink. Maybe you then can go and ask Professor Zeilinger directly. Is that okay? Okay, now I would like to give the floor back to the chair of tonight. And thank you very much again, Professor Zeilinger, for your talk. Of course,
we don't let our speakers go without offering them some presents, some tokens of appreciation. Over dinner, you were already given the book by Pieter van der Kruijt, who's written the biography of Jacobus Kapteyn. So that's gift number one. Gift number two is a book. It's entitled Dutch Light, and it's written by you, Elder Z. Williams. It's about one of your predecessors, Christian Huygens, one of the founding fathers of the light, of the wave theory of light, I should say. It's a wonderful book, and that's my second gift, please.
Thank you very much.
Okay.
Thank you.
And of course, this is the 10th Kapteyn Lecture, and the lecturer who presented the lecture is given a medal with the counterface of Professor Kapteyn. And this is also yours from now on. Please.
Okay, thank you very much.
Okay.
Thank you.
Nog een keer. Okay. Okay, thank you. This ends the evening. Thank you everybody for coming here. And of course, we would not let you go without offering you a present to everybody as well, at least the people in this room and the room next doors. And that's the drink that you can get for yourself for free when you at least go downstairs. Thank you once again, and have a good time visiting home. Thank you.